Good evening everyone. My name is Renuraman Sahu and today we'll be briefly discussing about what was taught in the last class by the professor. So mostly we saw that in last few classes we looked at the electrons in a metal and we told that those electrons are free. Free in the sense they do not see the ionic cores of the solid. So we first looked at the Drude model and told that the electrons are like the gases and gases, the classical gases, they follow the Maxwell-Boltzmann statistics. That means that comes from the fact that the classical particles are identical but they are distinguishable. On the other hand, what we see in reality is that electrons are the quantum particles, so they are identical and indistinguishable, and they follow something called the Pauli exclusion principle, and because of that they follow a statistics called Fermi-Dirac statistics, and as a result of that and because we incorporated this Fermi-Dirac statistics, what we finally got, that we got the correct value of the specific heat of the electrons. Earlier when we had used the Maxwell-Boltzmann equation or the normal Drude model, we saw that the CVE, this was 100 times more than the actual value. But now with introduction of Fermi-Dirac statistics, it was rectified. So these models basically, so what was the common in both of these models? They, in both these models, the electrons were assumed to be free electrons. So what free electrons means, suppose this is a solid, so we had, suppose this is a solid and it will have some ionic cores, and each of these atoms will actually give an electron, and those electrons will move around freely in this boundary of the solid. So that was the free electron model, where the electrons was not seeing the solid, the ionic cores in the solid. But in reality, so that is why these are the free electron models what we saw in the previous two models. But now what we will see is, we'll add one more layer of complication to it. Now we'll say that okay, now electron, let us say that electrons will see the ionic cores. So these ionic cores, so that brings us to the next level of complication, and before that we'll see that these ionic cores, they are arranged in a very particular way, and when this arrangement is over a very long scale, for example here, let's say this is a solid which is this single crystal, where the arrangement is very ordered, like here I am just drawing a square lattice for the sake of demonstration only. So here these dots are like the crystal lattice and where the atoms are there. So here you see very periodic arrangement if it is there over a very long scale or a large scale. Large scale in the sense this is like of the order of 1 meter or something, 1 meter or tens of centimeter. So basically a single, so this is basically a single crystal. So where you have very high degree of periodicity. High degree means periodicity over a very large length scale. But in reality what we see is that, suppose some crystals are there, but that solid will be a collection of different crystalline arrangements. So in that case we'll say that it is polycrystalline. For example here, within a single boundary, if you see at the second figure, a single boundary, it may be crystalline in, the crystals are arranged like this. Let's say here the crystals are, let's say these are arranged like this. Here the crystals are somehow differently arranged. Here it is arranged some more differently, and here some other random orientation. Okay, so this is called the polycrystalline solid, where it is, this solid is an aggregation of many crystalline parts. Okay, so but here if this is of the order of, let's say like one this crystal is of the order of tens of centimeter, let's say 1 meter, and these crystalline domains are of the order of, let's say, few centimeters. Then we say that it is a few centimeters or like few millimeter even. So these are polycrystalline with large crystal sizes. Here what will happen, if you so let us talk about a single crystal first. If you know the order at one edge or one location, you know what is the order at or the arrangement at a very different location. Here you see the length scale. Suppose if you know the order at this point, at this edge, then the maximum order that you can go is this. Here you know the arrangement. Now here if you look at the third figure, here the domains, the crystalline domains are further less. So this also you will say polycrystalline with small crystal sizes. Now when you, and these crystal arrangements are really random in orientation. So this type of solid are called polycrystalline with small crystal sizes. So this is what we discussed here. Like a single crystal will have periodic arrangement over a very large area. So this is a single domain, single crystal, because the crystallinity is entirely there. There is no cleavage of the atomic planes, and because of that, what happens if, let's say, there is an atomic arrangement in which it is kind of a rectangular lattice. Okay, it is somewhat like this instead of a square, and then you try to measure the properties. For example, let's say resistance or the refractive index, whatever it may be. Then the properties of the materials which are particularly dependent on the electrons, they will be dependent on the direction. For example, you measure the resistivity along this direction and along this direction, they will be totally different. So, but here, and that difference in properties with change of direction, that is called anisotropy. So anisotropy means you measure a property, refractive index or resistance, or like whatever the property may be. If it depends on the direction or the orientation of the crystal or solid, we say that it is anisotropy. When we look at polycrystallinity, polycrystalline with large crystal size, then we will see some anisotropy. So what? So anisotropy, the degree of anisotropy means, for example, it is highly crystalline material, let's say, and we measure resistivity R1 here and R2 here along this orientation. So the difference delta R will be the largest for this crystalline size, for this crystal. Here delta R will be little less than this, and here the resistance will be averaged whether you measure along this or along this. So so instead of resistance, like let's say this is resistivity, you measure along this direction, in this direction, the difference will be largest for the anisotropic, and when there is no difference, we say that it is isotropic. So in isotropy, because all the individual crystals may have the directional dependence, but as soon as you go to the next consequent crystals, they will have some other direction, other orientation. So over a large length scale, these properties get averaged out. So in a crystal, in a single crystal or a solid, we expect there should be some anisotropy. Whereas the free electron model, it was showing no anisotropy at all. So free electron model, if you remember, what is the conductivity? It was Ne square tau by m, Ne square tau over m. Here there was no parameter which will tell you about the direction. But as long as you introduce this crystallinity, you will have directional dependence. So that is about it. Now let us see how. So how does this electron see this ionic cores? Ionic cores. Because that's where, like, what is the source of this anisotropy? That source of anisotropy is basically the arrangement of the atoms. If that arrangement has some anisotropy, the electrons will see that solid, that ionic cores arrangement, and hence the solid will be, hence the properties will be anisotropic. So let us now look at how the electrons will interact with this ionic cores. Before going into detail, let us first look at how a single electron will behave with uh, a single ionic core. So here at the center, what I have shown you is this is a ionic core, the location of the ionic core. When the electron is very far away, so first, how does an electron will interact with a ionic core? Like you know about you can answer this, right? How electron and an ion is basically, it will be a positively charged particle. How will they interact? Any idea? Yes. Can you speak a bit louder?
Are you talking here or is it Coulombic or
Yeah, I mean there will be an Coulombic interaction. Yeah, somehow I'm not able to hear your voice nicely. Okay, so yeah, but it is like you're right. It is Coulombic interaction. So Coulombic interaction, it goes as and the potential corresponding to this Coulombic interaction. So the electron will experience a potential. That potential is basically minus 1 by 4 pi epsilon naught charge of the ion. Let's say it is, I'm just writing it as E only, by R. Okay, this R, when this R is too large, so in this direction we are varying R. When it is too large, then U goes to 0, but it is negative, you see. And when it comes towards the ion, so R will become smaller and smaller, and at this location, at the ionic core, it goes towards minus infinity. Okay, so as this distance decreases, as the distance will decrease, the potential will also keep decreasing. Similarly, from the other side, if it comes, it will start decreasing towards minus infinity as it approaches the ionic core. So this is about a single electron looking at a single ionic core. But in a solid, it will have a periodic arrangement of those ionic cores. So let us look what will happen in that case. So now we have, let us take the example of 3 ionic cores. This is one ionic core, this is one ionic core, and this is one ionic core. And corresponding to this ionic core, the potential is just this, the one which I am tracing with the laser pointer, this and this. Okay, then for this ionic core, the potential is this, it is coming like this towards minus infinity, and this. For this ionic core, it is coming like this towards minus infinity, and this. But when we look at the overall solid, what will happen? Let us say the electrons is too far away from the solid, it is seeing nothing. But when it enters the solid, it will first fall in the potential well of the first ionic core, and then when it comes to the next, what it will see is the next ionic core. So here what you see, it will, as it goes further away from the first ionic core, the potential is increasing. But as soon as it sees the next, so it sees the next ionic core, it is now in the well of the next ionic core. So it will again start decreasing, again it will increase as it goes away from this. So this cycle will continue. Okay, and what we will get is finally, so what it sees is basically this red color, this red colored potential set. To study this, so this is actually very complicated, because like the mathematical form of this will be complicated, and we don't have to know. So we will do an approximation of 1D crystalline solid, and we'll see what are the inferences we can get and how do we model this behavior of this ionic cores. So here what I have drawn here is a typical is an approximation of the previous model that we saw. So here are the ionic cores where these black dotted lines are there. This is one ionic core, this is one ionic core, this is one ionic core, this is one ionic core. Okay, so when when we say that electrons are free electrons means the electrons actually doesn't see the solid. So it is out of the solid when we say it is free electrons. But as soon as it enters the solids, it exists in a, so till here it is free electron, it is out of the solid. The boundary of the solid starts from here. So as soon as it is in the solid, what will happen? It will see it. So there is a little drop in potential. This drop in potential. So from here, it saw that drop in potential, and this potential, this U-shaped thing that you see here, that is the atomic well. The potential dip produced by the ionic core. Then here it is a bit free here, then again another well. So these atoms are approximated with these square wells, and in this length where just above the well and inside the volume of the metal means from here to here. Outside the metal means potential 0, inside the metal is negative, and at the atomic core we are saying that it is deeply negative, it is like very deep. The electrons, so we talked about the electrons donated by the valence electrons donated by by each ionic core, each atom. So each atom which will give that electrons, and it will belong to the entire, sorry, it will belong not to a single ionic core. So those electrons are free to move around in this entire length. So that we called free electrons when we studied about the Drude model and Drude Sommerfeld model. Now what we are going to say, free electrons are those which are not inside the solid. Which are inside the solid, from this boundary to this, that we will call a nearly free electron. Why nearly free electron? Because those electrons are not exactly free, they are free in the limit of this. In the limit, they are inside the solid. And the electrons which are bound electrons, or the electrons which cannot move away from the ionic core, so the electrons which are deeply bonded to the nucleus, those are the bound electrons, and those electrons are inside this boundary. Those are called the bound electrons. So we have now three types of electrons. The bound electrons which are confined in this well, they cannot move out of this well. Like here there will be some bound electrons and one electron, and there would be one electron this ionic core has donated to the free electrons, to the nearly free electron. So the three types of electrons are like this bound electrons which are confined to each of this well. Then there are nearly free electrons which is confined to the volume of this metal, and there are so these are nearly free electrons, and there are free electrons which can actually which are out of the boundary of the metal. So based on this, so we'll see certain important quantities based on this modeling. So we are saying that the boundary of the metal is from the point where, so it is, the electron is outside as long as the potential is 0. So here the boundary of the metal starts, and from here it goes on till here. So this length L is the boundary, is the length of the metal, or the boundary is the extent of the metal. This length A, the small a, is the extent of that ionic volume. And now, since in this direction it is energy, okay, so we are starting to fill the electrons in these energy levels. So there will be the energy levels of this free electron, and the highest energy level that can be filled is your Fermi energy. That is what we saw in the last class. So in the last class, if you remember, just for your recollection, I'm drawing it here. We saw that the occupation probability F of E and E along this direction, it was something like this, where this was falling at around EF. This EF is the Fermi energy. So what is EF? EF is the energy level which is occupied at the highest energy level occupied at 0 Kelvin. So there would be some energy levels for the bound electrons. All those are filled, and the energy levels. So this energy level that you see in the blue line, that is the highest energy level, let's say. So that is your Fermi energy. And potential, as we had discussed, potential equal to 0 means it is free electron. Now if you want to take an electron out of the solid or out of the metal, then you need to give certain threshold energy. That threshold energy is called work function. And what would be that threshold energy? That threshold energy will be the difference between this blue line and this black line, this EF and 0. Okay, that difference is your work function. That difference is your work function of that metal. Okay. So this is about it. And here the typical length scale of L is of the order of 1. This is of the order of 1 meter. 1 meter or tens of centimeter. Whereas this A is of the order of like a few angstrom or few tens of angstrom or nanometers, less than nanometer. It is of the order of angstroms. So that is what we have here. So you see the difference in this order of magnitude. So 1 meter and this is 10 to the power minus 10 meter. So almost a difference of order of magnitude of 10 to the power 10 is there. So the point to make here is that there are large number of these wells, and the electrons actually sees a very periodic structure. Now what we are going to study is, we will study at we identified 3 types of electrons. One is bound electrons. Bound electrons are the electrons which are confined in this square well potential. Then we saw about nearly free electrons. Nearly free electrons can move from in the extent of the metal, and they can freely roam around in this extent of L. Okay, so these nearly free electrons can move around in the extent of around 1 meter, and bound electrons can move freely only in the extent of a few angstroms. So that is what about it. Now we will look at how electrons will behave in a single potential well. But before that, we will look into some of the notations. And this you have already learned. What is a de Broglie? What de Broglie told is that an object with momentum p, it has associated wavelength of lambda. Lambda is given by h by p, or p is nothing but h by lambda. So what I am doing here is just a bit of arrangement. So I am dividing and multiplying by 2 pi. So this h by 2 pi is called h cross, or so it is just a notation for h by 2 pi is h cross. And 2 pi by lambda is called wave number. It is denoted by k. 2 pi by lambda is called the wave number. So p is nothing but h bar k. Now we will look at the momentum. Momentum, we know that it is m times v, mass times the velocity, and energy is nothing but half m v square. Now if you multiply m on numerator and denominator, what you get is half m square v square by m. So mv is p, just replace that. So what you get is E equal to p square over 2m. And from equation 1, you know that p equal to h bar k. So E equal to h bar square k square over 2m. So here what we got is a relation of energy with momentum. Momentum is k. Why k? Because h bar is a constant, so p and k are interchangeably used as momentum. And k is actually called the wave number, and p is your momentum. So now and we know that each and every particle, by virtue of this de Broglie principle, each and every object has an associated wavelength in it, but we want to understand what are the allowed values of this lambda for electrons in a solid. So once we get what are the allowed values of lambda or what are the allowed de Broglie wavelengths, then we can ask. So we saw that energy spectrum will be discrete. So if there are only certain number of or certain lambdas allowed, then the energy will be discrete, and that relation between how energy is related with lambda, or in other words, how energy is related with k, that is called a dispersion relation. So that is what we want to find, uh, and that will give us insight into how the electrons will behave in a metal. So now, before understanding the behavior of electrons in a metal, let us first look into a particular example of a string attached to a wall. Suppose there is a string, and here it is clamped only at one point, whereas the other end is totally free. Here, what are the allowed wavelengths? For this system, all the wavelengths are supported. Like whatever the wavelength you give me, so for example here, it is a very small wavelength. So the string can take this wavelength, or the string can take a very long wavelength such as this. Okay, you just follow the pointer, it is like it is a part of that wavelength. Okay, and here it is a mixture of different wavelength. So the string, a free string, it can take any wavelengths or any value of lambda as possible. Since now we have from de Broglie wavelength, so from de Broglie principle, E equals h bar square k square by 2m, and k is 2 pi by lambda h bar square by 2m, and this is 2 pi by lambda whole square. So since lambda can take literally any value, so the energy for this system is continuous, or there is all the values of energies are allowed. On the other hand, let us see what will happen if we confine this string. So here is a wall, here is a wall, here you have a wall, and here you have a wall, and the string is clamped at here and clamped at here. Now the constraint that you have is that x, or the displacement at x equal to 0 and is 0, and the displacement at x equal to a is also 0. So here the string is clamped, and how it can oscillate? It can oscillate, the string can have vibrate like this, like a single mode, or it can vibrate like this, or it can vibrate like this. So these are the different modes, as long as we are keeping the displacement at the beginning of the wall and the end of the wall as 0. So that is the constant we have now. So now let us look at what is the largest supported wavelength for the string clamped at two ends. So here you see this red color line is the largest supported wavelength which can be there in this clamp, in this setup. So what is this? Is half the wavelength. If if you trace this cursor, then the full wavelength is it will somewhat look like this, which is how it is related to a. A is the length of this distance between these two clamps. So lambda is twice the value of a is equal to 1 wavelength. So lambda equal to 2a, or a equal to lambda by 2. So this is a half wavelength. Okay. Now let us look at the second largest wavelength. The second largest wavelength is this lambda. And how is it related to a? So 1 wavelength is equal to a, or a is equal to lambda, or a is equal to 2 lambda by 2. Similarly, the third largest wavelength is, this is 1 lambda by 2, 2 lambda by 2, and 3 lambda by 2. So a is equal to 3 lambda by 2. Similarly, the next one will be 1 lambda by 2, 2 lambda by 2, 3 lambda by 2, 4 lambda by 2. So the next one will be 4 lambda by 2. So basically what we see here is that the length of this clamp, this a, has to be an integral multiple of lambda by 2. Okay, so this point is clear, right?
Yes, sir. Yeah.
Yeah. So the length A has to be an integral multiple of lambda by 2. This is the constant we are getting when we impose that the string is clamped on both ends of the wall.
So it's basically based on the wavelength. Sorry, yeah, wavelength. It's a half the wavelength is lambda by 2. So that's based on that your
Yeah, exactly.
steps of it. Yeah.
Yeah. So that's the thing. So I hope this relation is clear. Now since we know lambda, what is lambda? Lambda. So a you can write it as just rearrangement of this n by 2 lambda. So I have multiplied and divided by 2 pi, and lambda by 2 pi we know that 2 pi by lambda is k. So 2 pi by lambda from here is n pi by a, that is k, and this k you can use in the expression of energy. Energy we saw that it is p square by 2m, p equal to h bar k, and k we are just putting as h bar square k square by 2m, and k we can put from here. So what we actually get is this dependence on n. Energy is now energy cannot take any arbitrary value now. It will depend on n. So what we saw here is that we have once we confined this string or the movement of this wavelengths, it led to the quantization of energy value. Okay, the energy is now varying in steps of, so it will be some n square time this. So you have to put n equal to 1, n equal to 2, and whatever the values that we'll get. So those are the discrete values. Whereas when it was free, this E can take any arbitrary value that we want depending on this lambda. So what we saw till now is that, so just to recap, we saw a realistic picture of potential experienced by an electron as a function of position in the solid. What was it? We just saw that it was, so it looked somewhat like this. So it started from 0 and here and here. So this is the realistic picture of an, so if this is the ionic core, ionic core, ionic core, ionic core, and this is the picture of the potential, the realistic picture. Okay, then we wanted a reasonable approximation of above. What was the approximation? The approximation is this. So we have this, and we approximated this as first we came here like this, then we got to the near, so this was free electron when the electron is outside the solid volume. Then we went to the free electron regain. Then we have one well, this well corresponds to this ionic core, to the one that corresponds to this ionic core, and this ionic core. Okay, I hope you're getting me. So this ionic core corresponding to each ionic core, so this is an approximation. Okay, so this is what is our approximation, and we recognized the idea of confinement of electrons. There are two types of confinement. One is nearly free electrons, where it is confined at the scale of m. What it means is, so this is your, okay, I'll just, so there are two types of confinement. One confinement is the nearly free electron confinement, which is in this extent. Okay, and it is of the order of around 1 meter, of the orders of meter, from here to here. Okay, and there is another confinement where the electrons are confined in a particular ionic core. These are the bound electrons, and it has an extent of the order of few angstroms. Okay, and then we saw that analogy on the string. There is no restriction on lambda or E if one of the end is fixed, and if the ends are fixed, then we saw that quantization of energy will result. That was till now. Now we will look at what happens with an electron. So this is what we got from the string analogy, what we got was this. This we get from the string analogy, where a is equal to n lambda by 2. From here you get lambda equal to 2a by n. Then we found what is the value of k. K is 2 pi by lambda, and when you replace this lambda by its value from this constraint, then you see e equal to h bar square k square by 2m. So this was a very hand-wavy argument which has analogy with the string. This is from the string. Now, when we want to do this in the quantum mechanical point of view, then what we have to do is we have to look at Schrodinger equation. Now, what is Schrodinger equation? It is a differential equation which tells about how the wave function of an electron will behave. The wave function, it is the variable, and it has the information about the states of electron in, and it is governed by this equation, and it is minus h bar square by 2m, then second derivative of the wave function plus v, it is the potential energy, v of psi is equal to E psi. It is analogous to, so this term is analogous to the kinetic energy term, this is the potential energy term, and this is the total energy. So we basically have to solve this equation. So for truly free electrons, let us look at what happens for truly free electrons. So when I say truly free electrons, it means the potential is actually 0. When the potential is 0, so V equal to 0, so this term will totally vanish away. Then all we have is minus h bar square by 2m d2 psi over dx square is equal to E of psi x. That will give you this expression d2 psi by dx square plus 2m by h bar square psi of x equal to 0. And since it is like, if you remember, this is of the form of the harmonic oscillator equation, and a harmonic oscillator equation, they have the solution as a linear combination of the cosine and sines. So we'll say that psi of x equal to a cos kx plus b sin kx. So now we are saying that psi of x equal to a cos kx b sin kx. When you do the derivative as second derivative of psi, then what we will have is you will just get minus of k square a cos kx plus b sin kx, and this is nothing but your original wave function. So that we will write as minus of k square psi of x, and if we take it to the left hand side, what we have is d2 psi over dx square plus k square psi x is equal to 0. Now if you compare this equation with the original equation that we got from Schrodinger equation, so what we had got from Schrodinger equation, what we got is this d2 psi over dx square plus 2me over h bar square psi of x is equal to 0. So this is what we had obtained. And now if you compare, here we have this k square term, and here we have 2me by h bar square term. So these two now has to be equal. So k square is nothing but 2me by h bar square, or k, so what we have here, and e, so basically e is equal to, if you just rearrange this, what you will get is e equal to h bar square k square by 2m. And since it is since there is no restriction on k, no restriction on the values of k, we'll say that all the energy values are allowed. Now let us try to plot this function. When we are going to plot this function, see this momentum, so k square equal to 2me by h bar square, so what will be the k? The value of k can be, so k is equal to plus or minus root under 2me over h bar square. Okay, I hope this part is clear. So it can take positive values as well as negative values. So it's clear, right, till now? So when we plot this E versus K relation, that's what we call
one quick question, sir. Like dou square psi by dou x square minus k square a cos kx. So
yeah.
I understood that you're taking a harmonic equation here.
Yeah.
So the harmonic equation, you're using the minus k square psi of x. Psi of x, I understand that's a cos kx, b cos sin x.
From here to here.
But where is this minus k square coming from? This is from the previous page, is it?
No, it is from this page only. I'll just show. Hold on.
k square.
See, you do a one time derivative here. Just will use yeah. You do a single derivative d psi by dx. What you will get? What is the derivative of cos kx? So you will get a minus, right? Minus
Yeah, minus k. Yeah.
sin kx. What is the derivative of sin kx? Plus
K
b
cos
k
kx.
cos kx. Now you
Got
do
it.
the derivative
Got it.
again. d2 psi over dx square. So a minus k.
A
Now sin
cos
kx.
kx.
Derivative of sin
Cos
is
kx.
k cos kx, right?
Yes. And
Plus
correct.
b k. Now
B
derivative of cos
k
is minus k sin kx,
sin kx.
right?
So here minus comes. Okay.
So here minus
So
k into k minus k square, and here also minus k into k
yes.
minus k square. And what you have here,
So
a
it
cos kx,
plus
a cos
plus
kx
b sin kx.
plus
Yeah.
b sin kx.
Got it. Got it. Yeah, that derivation I didn't notice. Yeah.
Yeah, it is fine now, right?
Yes.
Yeah. So this we are so this is minus k square psi of x. This we are comparing with the Schrodinger equation. Schrodinger equation is what? I'll just write it for.
H cross square by 2 pi minus h cross square by 2 pi
Yeah.
into
So after we put v equal to 0, what we had got is d2 psi by dx square plus
dx square
2me over h bar square psi of x is equal to 0. This is Schrodinger equation for truly free particle. When I say truly free electron, that means v of x is equal to 0. Okay, when v of x is equal to 0, this is what we have. Now you compare these two situation. So this thing will be equal to k square. So that is why k square equal to 2me by h bar square.
yeah
Fine.
tme by h cross square.
Yeah.
Yes.
And so k, now if you, this is k square is this. From here you can write k is equal to plus or minus square root of 2me over h bar square.
Yeah.
This k can take literally any value, positive to negative, there is no restriction on it. Just look at the graph, it can take any value. So since there is no restriction on k, energy can take any value. As you increase k, energy will start increasing. Okay, so here for the free electrons, energy have the continuous, energy is continuous. Now what we are going to do, we are now going to confine the electrons. So now let us look at electrons trapped in a potential well. What we are basically saying is that, so this is a potential well, it starts from 0 to A, and outside this electron is not there. That means outside this boundary, so this is the boundary of the, so this is let's say position x. So electron is available only between 0 to A. Outside there is no electron. That means whatever the wave function we will have, that will be identically 0 outside. The wave function is 0 here, the wave function is 0 here. Here inside what will be the wave function, we will try to figure out. Okay, that we will figure out from the Schrodinger equation. What is inside we don't know yet, but we know that. So according to this particular problem, we are saying that electron is found only between 0 to A, and not anywhere outside this potential. That is our concern. So how are we going to find what is inside? What is inside? We can, so we know that this will follow. So we know that psi of x equal to 0 outside in this region, and here psi of x is equal to 0. You see, psi of x equal to 0 is a solution to the Schrodinger equation anyway. Psi of x equal to 0, you put 0 here. put in all these three terms, it is satisfying. So outside it is totally satisfied and it meets our requirement. But now what we want to do, we want to find psi of x inside. Okay. To do that, what we do is we again solve this boundary condition. We again put this, and then we'll put v equal to 0 inside the well. This is what we have. And since v is equal to 0, again we have this minus h bar square 2m d2 psi over dx square, d2 psi over dx square plus 0 is equal to e of psi. Okay, and when we take this 2m to the right hand side and rearrange the terms, we end up with this equation. Again the same equation, d2 psi by dx square plus 2me over h bar square psi of x is equal to 0. This is again the same equation, and similar form of solution will hold psi of x equal to a cos kx plus b sin kx. But now, so in the previous case there was no boundary conditions. Now we have the boundary condition that psi of 0, so at this point the wave function has to go to 0, and at this point the wave function has to be 0. This is like you are clamping the wave functions. Okay, so the wave function has to be 0 on this end. So we have to impose these two conditions on this solution. So this solution is there. We have to put psi of 0 equal to 0 and psi of a is equal to 0. Now let us do that. Just a minute. Yeah. So what we are going to do, we are now going to apply the boundary condition. The first boundary condition is psi of 0 is equal to 0. So at the position x equal to 0, the wave function is 0. Now what was our solution? A cos kx plus b sin kx. So a cos, since x equal to 0, so it will be a cos 0. So cos 0 is what? 1. So and sin 0 is 0. So what we are left with is a is equal to 0. Okay, now let us look at what happens at psi equal to a. At psi equal to a, we have a cos ka plus b sin ka equal to 0. But now we have found from the first boundary condition that a is 0. Since a is 0, this term vanishes. Now we are left with b sin ka is equal to 0. Now this can be 0 only if this sin ka is 0. B can take any arbitrary value. And when can this be 0? Sin ka is equal to 0.
Sin k is 90.
Not only.
Oh, sorry, 0. K is 0, yeah.
When ka is, no, sine, if you look at the sine curve, how it is?
180 and 0, right? Or
At 0, at 180, and let me just draw it for you.
360.
So sine curve, how it looks like? It looks like this.
Sinusoidal, yeah.
Yeah. So this value
Pi
is
2
0
pi.
degree. This is 180
Pi 2
degree.
pi, yeah.
This is 2 pi. This is 3 pi. This is 4 pi. So in general, it is n pi. You got it? Where the sine is getting 0.
Yes.
So sin ka equal to 0 means this ka has to be n pi. This point is clear?
Yeah.
Yeah. So now we got that k cannot take any arbitrary value. It has to be n pi over a. It has to take this. So once we are confined, once the electron is confined in a volume or in a length of a, then k can take n times pi by a. So and remember that this has the unit of 1 by length. A has the unit of length. So k can take the value. These values only, not any value in between. It cannot take 1.1 pi by a or 1.2 pi by a. It will take 1 pi by a, 2 pi by a, and so on. So now
N is integer.
So now it has become discrete or quantized. And when we look at the energy is nothing but h bar square k square by 2m. And when you put the value of k, h bar square by 2m, and it is pi square n square by a square. See, this h bar is a constant, m is a constant, a is a constant depending on what the material is, and it is now increasing in steps of n square. So now previously when it was not confined, electron was continuous. Now how it will look like? Now see, k
It's
cannot take
bounded.
any arbitrary value.
Bounded. Yeah, it's a
K can
bounded.
take only these values, pi by a, 2 pi by a, 3 pi by a, and so on. Okay, and the energy is now discrete. Energy can take either this value. So here actually, if you see, it is symmetric along x and y. So this value is same as this value. It is, this value is same as this value. Okay, this is actually same. So this is, so energy can take these values. So it cannot take any arbitrary value. So what we learned here is that confinement led to quantization of energy. So this is the energy that you have, and it is to be connected to this. Okay, and these are confined in the length scale within a. That means the value of k that you have is n pi over a. Okay, and if the electrons are confined within the, now just imagine what will happen if you increase the value of a. As you increase the value of a, then this gap will start decreasing, right? Are you getting the point? What will happen if we,
Yes.
so these points will come closer and closer and closer and closer and closer. So when,
Yeah.
now imagine this L, so what in the case of free electrons, what we have? In the case of free electrons, we have that it was a continuous parabola, isn't it?
Yeah.
You remember this plot, right?
Yes. Yes.
This plot I'm talking about. Where is it? Yeah, this plot. Here it was totally a parabola and it was totally
Parabolic curve.
continuous.
Yeah.
Now when we have, now when we discretized, then what we have is it has, so it is discrete, and but it is still
Yeah.
on a parabola. When you increase the value of a, or the increase the volume of confinement, what we have is these points will come closer and closer, and it will tend to be continuous. Okay, so when we say that electrons are bound within L, L is, you remember that big L, which is the volume of the metal. There
Yeah.
the bound electrons will be like, the dispersion relation of bound electrons, these are so closely spaced. So imagine that, so see, L is around 10 to the power 10 order of magnitude larger than A. So this gap will become 10 to the power 10 order of magnitude smaller. So this is so small that you will think that it is continuous only. So that is why we said that the electrons which is bound within the volume L, those are the nearly free electrons. You understood this
Yes.
point?
Yes.
Yeah, cool. So that is why those electrons are called the nearly free electrons. So that is all about this. So what we saw in this three, in the last three classes is about this. So the different types of confinement. Based on this, we can have some discussion of question answer. So okay, now tell me what about this. Uh, what shows perfectly atomic orientation and different properties in different directions? What is it?
Anisotropic, which is single crystal is completely anisotropic.
Yeah, perfect.
Polycrystal with polycrystal with few large
So it is showing
crystals will
perfect
be
atomic orientation. Okay, look at the word perfect.
okay. Then we should not have yeah, few large crystals is fine, right? Random orientation is not okay here.
Random orientation is not okay, totally not okay, but it has to be perfect. Since it is perfect, it will be only single crystal.
Okay, got it.
Okay. What about this second
Okay,
one?
so second one, polycrystals with much smaller size and randomly oriented crystal have dash properties. Randomly oriented will be isotropy, with
Perfect.
while graphene material shows
So graphene is a 2D material, just for
graphene.
your information.
Yeah, that will be anisotropy, right?
Yeah, perfect. So it is
So
isotropic and
isotropic and
anisotropic.
anisotropic.
Yeah, this is your only correct answer. What about
Why
this?
suddenly graphene is taken here in this example?
Actually, professor has talked about graphene as an example of anisotropic. I forgot to mention in the discussion.
Ah, okay. Okay, sir.
Yeah. What about the third one?
Potential energy of electron approaching towards ionic core is zero, and at infinity becomes infinity, right? Or no?
Potential
Becomes
energy of a free electron approaching towards ionic core. How does it look like if you remember the plot? It is just U
yeah,
equal, the potential equal to minus E over 4 pi epsilon naught R. This is your
1/r.
expression.
Yeah,
So when potential of a energy of a free electron approaching towards ionic core. So this is an ionic core, let's say, is
yeah.
potential energy of, and at infinity it becomes, at infinity we know that it becomes zero. Okay.
Zero. Yeah. Then it is
And it is
infinity and
approaching towards
zero,
the
or
ionic core. When it approaches towards the ionic core, it keeps on going down, down, down.
increasing. Yeah.
So it keeps on decreasing. So
Oh,
it
it's decreasing. Yeah, yeah.
it will be decreases and zero.
Decrease and zero. Okay. Okay. So I have to look at the curve in this way. Okay. Okay.
Yeah, it is
It's negative
approaching, no.
potential energy.
So what the potential energy of a free electron, you have to look at this word. Free electron approaching the ionic core. That means the R is decreasing, right? So
Yes.
there is a
Yes.
free electron, its potential energy like this, like this, like this, and it is decreasing, 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 so like this.
So in ionic core, we don't have it in. It is not considered in Drude model or a Drude Sommerfeld model. We
No,
had.
in none of the Drude model or Drude Sommerfeld model had ionic cores, right? They were just saying that
Yeah.
electrons are just free electrons and they don't see the ionic cores at all. But here
So
we,
infinite potential well measurement that has ionic core, right?
the infinite, yeah, the infinite
Potential
potential
well.
well is that we studied because we want to model, because we wanted to model uh, this potential. So this potential is a realistic potential and it is really very complicated. Rather what we want
Yeah.
is, we wanted to simplify it, and what we did was we just, here what we did was this, we just did this. Let's say this is the potential, that's what we did.
Yeah.
Okay.
Yeah.
So that is why we
So instead
wanted.
of infinite potential well, we took this
So
well.
this is a finite potential well. If you, so this is a finite potential well, right? We wanted to look at a
Yes.
particular extreme, what will happen. So we'll say that, let us say that this is so deep, this is so deep that we just want to study only this part, the bound electrons. So
Yeah.
for that we approximated and we tried to study the infinite potential well. That was the motivation.
Okay. Okay.
Now what
So,
about
but that
this?
has a core, right? That has ionic
Yeah,
core.
yeah, that has the
In
ionic
infinite
core. Yeah.
potential. So basically, one see when an electron process from one to another end, right? Um,
Huh.
it feels different because of the ionic core, or it because of the it's because of the ionic core, right?
It, because
It
of the
actually
ionic
sees
core,
the,
it sees the difference in that modulation of the potential that you see. It is because of the presence of those ionic cores.
and we don't have to say it as a bound electron.
See, we discussed about three types of electrons, right? Inside the metal it is there, then it can be
Yeah.
uh, either nearly free electron or it can be a bound electron. The nearly free
Yeah.
electron, it can move in the entire volume of that metal. But the
Yes.
nearly free the bound electron, that can move only near its or parent atom. So
Yeah.
how is the model that we had thought of? So there would be a collection of atoms, and each atom will give an electron, and once that valence electron is given away, then what we have is, that valence electron is free, so it doesn't belong to the parent atom anymore. It is free to move entirely in the solid.
Yeah.
So that's what it is. Okay. Okay, now what is the fourth question? How will you answer it?
In a meter long solid, nearly free electrons are free to free to run. Just now we discussed free to
Ye-
run across the solid,
Yeah.
confined to the ion core.
Yeah. What else?
Bound electrons are confined to the electrons. So, but in solid, in typical solid,
Yeah.
um, the effect of movement is only from the ionic core, not because of the bound electrons. We don't say it as bound electrons, right? That was my question earlier.
No, no. Ionic
We
core
call it
means
free
what?
electron.
See, suppose we have a nucleus, then there will be
Yeah,
some core electrons, and there
correct.
will be one valence electron which is the outermost. It is very weakly
Yes,
bonded. This is a
yes,
single atom. Okay, so these are core electrons.
yeah.
Now,
So the
when this is given away,
restriction in this, yeah,
this is given away, then what we draw
become,
in a solid, what we draw
yeah,
is these points that we draw. No, the single point corresponds to the nucleus and the bound electrons, which cannot move away from this nucleus. It is bound to
yes,
the nucleus. That is why they are known
yes,
as the bound electrons. And
yeah,
this has an overall positive charge because it is now no more neutral. It has given away this electron. That is why it is an
yeah,
ion.
correct. But what my question was like, the difference in the environment for each electron will be caused by the bound electron, or is it because of the ionic core? Ionic core only, right?
Yeah, the ionic core.
Ionic core causes,
The ionic
yeah,
core is nothing but the nucleus plus the bound electron.
nucleus, nucleus.
No, no. See, the nucleus and the bound electrons, they both
Hmm.
constitute the ionic core.
Okay.
You get it right? The ionic core means what? This nucleus
Oh,
is
it is the
anyway
bound
positively
electron
charged.
and nucleus together.
Huh?
Ah, okay. So it is bound electron and ionic core together. Sorry, bound electron and the nucleus together forms as the
Ionic core.
um, okay.
Ionic core is,
So ionic core itself is not the,
yeah.
so which is the contributing? See, if you take these three as variables, which will be the major contributing for the electron movement within the solid?
So within the solid, what the, okay, I'll just draw it again. Yeah, so this potential, if you just take the nucleus, okay,
Hmm?
so these are just the nucleus in an atom. So they will be like this, just the nucleus.
Yeah.
These are just the nucleus, okay. Now your question is, so based on this, like I'll try to draw our model also.
So if I have an electron
Yeah,
within this solid nucleus, solid, consider this as a solid.
yeah,
Okay. If I have a,
yeah. Tell me.
yeah, if I have electrons moving from one end to the other, what will restrict the movement of the electron? It is called a nearly free electron, not the free electron by itself.
Yeah,
Or,
see, for example, if you consider this area, okay, this area. So this you have a nucleus. I will just so what will restrict the movement is the charge, the overall charge of the. So one electron cannot go away because if one electron just goes away here outside the metal, then uh, the
it
coulombic
becomes
attraction
positive.
will be so much that it will again pull back to here inside the metal only.
Yes. Now my
So
question was like the free electron movement within the solid itself
within the solid
will be
itself,
controlled by, yes.
it is not controlled.
Is
It
it
is free,
controlled by
no? I
the,
mean, what do you mean by control?
yeah, but what makes it restricted to, move within the solid itself? It cannot move randomly. It can
Y-
only,
Yeah, yeah. Oh, okay. What defines that solid boundary? So that is again a coulombic interaction only, the coulombic attraction.
that's
But there
ionic
has to
core, right?
be,
That is because,
yeah. I mean, it is the Coulombic attraction, but still it is in a bound state. What it means is you will have an energy level. So I will tell you, you will have an energy level. So this is because of this Coulombic attraction. There will be an energy. So this is the energy of the environment. Oh, wait, it is like this. Okay, sorry. Yeah, I will just tell you. Yeah, I got your question now. So the free energy is this. The environment energy is this. But the energy of the free electron will be somewhat less than the natural, so less than the free electron, original, actual free electron. You need to supply at least this much energy. This energy is called work function. It is inside
Yes.
the, so when we say it is nearly free electron, it the energy level of that nearly free electron is underneath the free energy. It is a negative energy. If you take this as zero potential, the energy of this nearly free electron is negative. And it is negative because it again the same quantum mechanical principle will come up. And so what is happening is, because of all these ionic cores of the metal, they will create a potential which you see here on this diagram. And the allowed energy level is less than the free electron. We say it nearly free electron because it is not bound, and not bound in the sense it has energy level more than that of this well. That is why these electrons can move from one well to other well. I mean, it can move around in the entire metal, but it cannot, it is not bound to one. That is why we say it nearly free electron.
Yeah.
Does that explain? It is just I mean, the confinement. Why did the confinement occur? The confinement occurred because of the presence of a nucleus, a positively attracting entity, which was nucleus here. And then what we saw, when similar potential is created by a collection of, like when the potential length is L, then also it is discrete. Are you getting it? I mean,
Yes. No, I understand now. Yeah. Yeah.
there will be still that energy level L, that energy level within which it will be filled. And there is this Fermi energy, right? This is the highest filled energy level. And that highest field energy level is less than that of the free electrons, which is still negative value.
Yeah.
You got it right?
Yes.
Yeah.
But my question was not that. My question was, what is restricting the electron movement? Is it the ion core itself or the bound electron?
Yeah, it is the ion core, no?
The ion core. That's not my question. Okay, I understand, because the core, the nucleus is what is attracting it, right? So that is only one which can restrict it.
Yeah, the nucleus is attracting the electron. It is just the Coulombic attraction. That's all.
Yeah, because see, at one point, for example, you have shown the green location, the electron will have some kind of a potential compared to the location in the well, the bottom of the well,
Yeah.
and the top of the well. So all this is determined by the ionic core, right?
Yeah, all these are determined this ionic cores.
Yeah.
Is that clear? Or,
Yes, sir. I think I'm clear. So another question in the same diagram you have here.
hmm.
Another question. If I have to call this location that you have put work function that you have put the green, no,
Yeah.
E minus
Yeah.
electron. So if I have to call that location as my potential energy, should I call that, or
That location
the
is,
location is the potential energy? Can I call that?
yeah, yeah. I mean, this is
Oh,
uh, so along x-axis, this diagram, in this diagram along x-axis is your position,
yeah. This is x, and the
and
top is
this is your
energy, right?
energy along this axis.
Yes.
Energy or the
So
potential.
for correct. energy of potential energy, right? Yeah. So now if I call this location 0, the location at which you have 0, or where you have put the arrow,
Yeah.
yeah, this location, what do you call that? Is it the potential energy you can call it, or you call that as a nearly free electron?
No, no. This
That
location we call
location.
the free electron. The metal starts from here. This you can say air or environment, whatever.
Yeah. So nearly free electron starts from this location, the
Then
red intersection,
the
red intersection.
from this point onwards, the nearly free electron starts from here.
Okay, so that is nearly free electron,
So from
and
here,
my
for the nearly free electron, the energy level has to be anywhere in between this level.
yeah.
Okay, this arrow has to be satisfied. I mean, within this level, whatever the, I mean, is it clear? Or look, I will go to here. In this diagram, if you see,
Yes.
is this the one? No.
No.
Yeah, here.
Yeah, this one. Yeah.
Here, any yeah, from here, the point where the laser pointer is to here.
Mhm.
If the electron
Yes.
has energy value anywhere in between this, then
Yes.
this electron can travel from here. So this is where the start of the metal starts. This is the metallic boundary.
Yeah.
Okay, left
So
side to this is free electron reclaim, which means
so
that
the
electron
blue
is
line to
the
the black line is my work function. The blue line to the black line is my work function, right?
work function. Yeah, the blue line is the Fermi energy. That is the highest field orbital. From here to
No, between the
the
distance between the black line and the blue line is my work
is
function.
your work function exactly. What it means is that you are giving certain energy to the metal, this electron, so that that electron comes out to this energy level, and when it has this energy level, it can move out to the surrounding easily.
Yeah. What is the lattice position in this graph?
What is the lattice?
Position. If I have to say lattice position,
Yeah, this is where
A.
one lattice atom is. This is where one atom is.
Okay.
Then here,
Each
wherever this dashed line is
dotted line.
intersecting, right?
Yeah, all the dotted lines are my lattice position.
Yeah.
And if I have to look at the location in the bottommost red color in the bottommost well, yeah, that is my bound energy.
So this is your potential well. I mean, this is
Yeah, that is
the
my bound energy. Can you call that as a bound energy or
no, no.
potential
This is
energy?
not bound energy. This is your well. This is your potential shape of
Yeah,
the potential. So your
yeah,
that means that the electron cannot have a potential energy lower than this. And when you solve this, then the energy levels that will come up is something that will look like something like this. This will be your energy level, this will be your energy level, this will be your energy level. Okay? Or like
yeah,
so so energy levels are discrete in the bound, right? That's what we saw. When there is confinement, energy levels are discrete. So you can take either this energy value or this energy value or this energy value and nothing in between. So these are, and when you start filling in the electrons, these electrons can move only in this extent. So these are your bound energy states.
yeah. And this this graph seems to be the biggest bound electrons. This is bound electrons. You're right. That I got it.
Yeah.
A and this line is okay. Electrons there are nearly free. Oh, it's okay. This red color starts. That's where the electron nearly free is there,
Yeah.
and bottommost is my yeah this thing bound electrons. Got it, sir.
Got it right? Yeah.
Yes, and I can call A as my potential energy.
A
The
is your
location.
potential energy. That is the length of your
No, the zero.
potential well. The small a, right?
The red zero that you have put here.
Yeah.
That location, if you consider that, I can take it as a potential equal to zero.
Potential
That's
is
a
zero.
free
Yeah.
electron. Free electron.
Okay. Now, so you are clear about this, right? So what is the typical value of L? It is of the order of 1 meter, or like tens of
Yes.
centimeter. Like it is chunk
Yes.
of metal. You say that.
Yeah.
It is that is why it is of the order of meters, and a single atom it is of the order of 1 angstrom.
Okay.
Okay, so that is why we have taken this value of A to be angstrom. So this A is of the order of angstrom, right? So that's what it
Sure.
is. So we'll now go to the question and answer.
Sorry, I tried to understand that
Yeah, yeah,
particular
that's perfectly fine.
graph
That's
better.
the purpose of the session, no?
Because
Yeah.
today I'm not outside. Like last two classes, I was outside in between, so I
Okay.
was, having trouble talking to you.
Yeah, yeah, no problem. Okay. Here, I think it is getting clearer with the discussion. That's the purpose of the discussion only, no?
Yeah.
Yeah.
Table below shows.
No, no,
This is
we
the
are
only
not done
answer,
with
right,
the
sir?
fourth question. What about the other three?
This is confined to the ionic core. No, it is not true. Free to move within 1 meter distance. That is not true, right? Confined to few
You
angstroms.
just read in a meter long solid, nearly free electrons and bound electrons. What is the extent of their
Yeah.
movement?
Nearly free electrons is free to run within the solid, right? That is
Yeah.
what we selected in the first one.
Yeah. What
But
about,
the last one is also correct.
yeah, it is multiple answer question.
No, my question is, since you said 1 meter and order of Armstrongs, that's what we discussed on the
Yeah, it is also
electron
saying no,
movement.
the near in a meter long solid.
Yeah, free me to me within the. Okay, got it. Yeah. So it's 1 meter within 1 meter distance and confined to few angstroms.
Yeah,
Few
so
angstroms is because it is bound electron. Okay.
yeah, that's the size of an atom. So this
Yeah.
option is also correct, and these are not correct.
Got it. Okay.
Okay. So, what about this fifth question?
Um, Fifth question says, table shows a condition and a result due to the condition. Based on these, pick the choices that apply. Truly free electron. No restriction on lambda that can be supported. Electron confined in a potential. Any discrete set of lambda can be supported.
So
Truly
what
free
about,
electron, lambda, the wavelength. So we have to go with the Schrodinger equation, right?
is A is true or not? First, tell me that. Truly free electron.
Yes,
This
true,
is true.
true.
Perfect.
Yes.
What about this?
Confined in a potential value. Any discrete set of any discrete set of, no, that is not true.
Not true. Why?
Because any discrete set is not supported, right?
Yeah, it is
Means
not any discrete set. It is that set which is given by the Schrodinger equation.
exactly. It has
Yeah.
to follow the Schrodinger equation.
Yeah.
Yeah.
Perfect. Perfect.
So A is true and B is
A
false.
is true and B is false. Yeah. This is the correct option. Okay. What
So
about this?
energy levels are more closely spaced in in a nearly free electron or a bound electron.
Yeah. You should tell me that. Let me just put
Closely,
another.
it's
Yeah.
bound electron, right?
Let's just understand.
Bound electron, because we discussed on that curve that we made 2 pi minus 2 pi we made, and then we
So
said if
E is
the
equal to what
spacing
we
is,
have? E equal to h bar square by 2m pi square by a square and n square. Here for bound electrons it is A,
yeah,
and
if A is
for
smaller,
nearly free electrons, it is E is equal to h bar square pi square n square by 2m. It is now L square. Now tell me where the
yes,
now now for the sake of this, L is equal to 10 to the power around 10 times A. So where the energy spacing is more, for the nearly free electrons or the bound electron? Now tell me this.
L is bigger, right? Yeah, 10 times bigger, yeah. So
10,
nearly free electron has more,
it has more energy spacing, very less energy spacing.
yeah, it has less energy in the nearly free electron.
So do you see the order of magnitude 10 to the power 20 times? So if the delta E is something here, then here
Yeah.
delta E of nearly free electrons is 10 to the power 20 times smaller. So it is almost
Correct.
continuous.
Yeah.
You get it right? How
In
closely
in which case it is continuous in the nearly free electron, right?
nearly free electron case, because the gap is really
And
very, this delta E will be very very small.
yeah, delta is very small. But can we call that as closely spaced, right? It can be called as closely placed in the nearly free electron compared to the bound electron.
Yeah,
And it is because of the large confinement range.
it is because of the large confinement range. Yeah.
Because it is very closely spaced.
Yeah, and that is the reason only when we go to the nanoscale we see these quantum effects. But the
Yeah.
quantization of energy was not there like before the technology had advanced to go to the nanoscale, right? Only when we went to the nanoscale, then we saw these quantum effects playing a big role. That's because this discretization of energy started. It began to matter in real sense.
Ah, okay. So discrete energy matters is where we have the Schrodinger equation supporting this variable. Okay.
Yeah. See, the quantum mechanical effects are there even in the large length scale. But it is, this energy spacing is so less that we say that it is okay, almost continuous.
Yeah.
Okay.
Yes.
Okay, now let us go to the next question.
Potential fell. Okay. It's completely different, is it?
Yeah, so what do you think about it? Is it visible?
Potential in a material can be at specific location is
Sorry.
of atomic dimension in some location is a representative of potential energy experienced by an electron under the influence of ionic course in the solid.
Yeah.
Yeah, last two is correct, sir. Is representation of the potential energy experienced by a electron under the influence of ionic course in the solid, and is different for a free electron and a nearly free electron.
So this is different. This uh, is of atomic dimensions in some location. Is this correct or not?
I'm not understanding that atomic dimension. Are we talking about the lattice energy?
This we are talking about the potential well in a material. Potential well in a material
Yeah,
is what? This this is what we are talking about.
correct. Yeah.
So okay. So can be deep at specific locations. Is this true or not? This is really deep.
Yeah, it can be deep.
This is
Yes.
true. Is of atomic dimensions in some, so deep, we talked about this depth. We talked about the depth now. With, it is really deep, so deep that we can approximate it as infinite potential well. So it can be very
Yes.
deep. Is of atomic dimension in some location. Some location, let us choose at this location. It is of the order of few angstrom.
Yes.
So few angstrom is of atomic dimension. So this is also correct. Now it is a representation of potential energy experienced by electron under the influence of ionic course in the solid. This is also correct. This you already answered. And it is different for free electrons and nearly free electrons. This is also correct. This is fine, right?
So all are correct. All are
All are
correct.
correct, yeah.
So for atomic, I felt the atomic dimension is okay, but can be deep at physics question. Okay, that's it's because we can the potential energy depth can be anything. Okay, got it.
Yeah. What about the next question?
Length scale of a freedom of an electron participating in photoelectric effect is not same as bound and trapped electron.
What is the length scale of free electron participating in photoelectric effect? So where does
Photoelectric
this
effect.
photoelectric effect, how does it happen? You give at least the amount of so the amount of energy that you give in photoelectric effect is your work function, right?
Yes.
So what is the length scale of that? So okay, let me just I'll make a few. So this is there, this is there, this is there. Okay. Now we'll make this energy level. So this is your Fermi energy, right?
Yes. Work function is between the zero and
Work
this. Yeah.
function is between this.
These two. Yeah.
Now tell me, electron participating in photoelectric effect, what would be its energy value?
E.
Its energy the energy value will be this, right? The one which
Fermi
is
energy.
Fermi energy, or near to that,
Okay.
some value near to that. That is the energy. And what is the
Why
bound
on
and trapped
photoelectric effect
electrons?
when you say photoelectric protection, what do you mean by that? That's
So,
here.
oh, okay, photoelectric effect. Okay, so what happens is photoelectric effect is an effect in which you have a metal. Let's say this is a metal. You shine some light on it.
Yeah, so the light passes and then you
No,
get the
no, no, no.
refraction.
So you shine some light on it. When you shine some light, then what happens? The electrons. So after a threshold frequency, so not all the frequency can excite the electrons. After some threshold
Yes.
frequency, the electrons will start getting ejected from this metal.
Yes. Yes.
That is the photoelectric. Photo means this light, electric means the ejection of the electron. So electrons get
Yeah.
ejected when you shine some light on it. That is your photoelectric effect.
Yeah. So
Okay.
the energy required to remove this electron is what we are talking about, work function here.
The least
Got
energy
it.
that is required to remove those electrons are called the photoelectric effect.
Okay.
And that is this energy, this gap that we are saying.
So bound and trapped electron in this case
Yeah, bound. What is
in
bound electron?
photoelectric
Bound electron is the electron which is bound to a nucleus.
cell.
So we saw that
Yes.
these energy values. These are the bound electrons.
Yeah.
Okay. So the length scale of freedom electron participating in photoelectric effect, and what is the length scale of freedom participating in photoelectric effect? It is L.
Yeah.
Whereas the length scale of freedom of an electron, so electron participating in photoelectric effect and electron which is bound and trapped is what? Those are these electrons.
Here.
These
Bound.
are
Yeah.
bound and trapped to their nucleus. What
Yes.
is the length scale of that?
A.
It is of the order of few angstrom. This is
Yes.
of the order of a meter or tens of centimeter.
Meters.
So
Yeah.
what it is saying, the length scale
It's
is
not same.
not the same. Is it true or not?
True. Yeah.
Yeah, it is not the same, so it is true. So this is true. Okay. So what about the next question?
The value of work function of a material is associated with the energy levels from below the energy level. A positive value.
A positive value, yeah. Why? Because you have to
Because
supply that energy.
yes.
Yeah, it is a positive value. Perfect. What about this question?
When a solid energy of an electron is not continuous when it is free to move within not continuous.
Energy of an electron is not continuous. That means energy is discrete.
Yes.
Now, when is that true? When it is free to move, it is not continuous. That means it is discrete.
Yes, it is a discrete electron. Yeah.
Discrete means electrons are bound.
Yes.
When it is bound from these conditions, is this condition, can you say it is bound? It is free to move within the distance minus infinity to infinity. That means entire, it can move around freely.
Total value.
Total
Yes.
value. Is
It is
this
not bound.
confined?
Yeah.
0 to infinity, it is confined or not?
No.
It is also not confined.
Only
Minus
the 2a. 0 to 2a
yeah.
seems to be that because that is Armstrong level.
Yeah,
Yeah.
so it is not only angstrom. The thing is, it is confined. As long as confinement
Yes.
is there, there is discretization.
Yeah.
Okay. What about the fifth question?
Schrodinger wave equation consists of kinetic energy and potential energy terms.
Perfect. This consists of one kinetic
So the
energy.
sum of kinetic energy and potential energy is our Schrodinger equation, right?
Yeah. So actually, what we say is the momentum. It is in quantum mechanics. This momentum behaves as an operator, and that operator is I uh, h bar over m dou
Yeah.
by dou x p square by 2m. No. So okay, this is the. So when you do p square, it means, so this iota is minus 1 h bar square d2 over dx square. So this is your p square.
Yeah.
So when you do
Yeah.
p square by 2m, psi plus v of psi is equal to e of psi. So these are now operators. These are operators that you, and when you write it in Schrodinger equation form, it is just minus h bar square 2m d2 by dx square psi of x plus v of x psi of x is equal to e psi of x.
EFX.
So it is just kinetic and potential energy.
So can we call this as a total energy?
Yeah, E is the total energy.
Yeah. So can we calculate the free energy of all electrons in this total equation?
Oh,
No, right?
what?
Can we say this as a free energy of all electrons? E of x, E psi of x equal to
Free
sum
energy.
of free energy of all electrons. Yeah. No, right?
No free energy. This is just the energy of the electron in that potential.
Yeah. It's energy of potential. Okay, got it. Yeah.
Yeah,
It's not the free energy
it is not the
because free
free energy.
energy will be, yeah.
Okay. What is the sixth question now?
A single A single crystal, when compared to a polycrystal of small grain size for the same material and phase, okay, a single crystal is small grain size for the same material and phase, it's more likely to display anisotropy. True.
True.
Will have the same crystal structure throughout the sample, unlike the poly. Correct. That is true.
Yeah, true.
Will
Perfect.
have the same crystal structure throughout the sample, just like a polycrystal. That is false.
So
Polycrystal will not have same crystal structure.
this is false. Okay. Six. Okay. What about the next question? Graphene.
Graphene displays anisotropy because of its crystal structure. That's what I can think of.
Yeah, because that's what it is.
Yeah, its relationship diamond is not there, right?
No, what is the relationship with diamond? It is just the same element. But because of the arrangement of the carbon atom in a particular way, it is in a 2D fashion. So that is why it shows anisotropy.
Okay.
It is
What is the
just,
advantage in graphene compared to other material? Why it is showing more, superior properties and conductivity and all that?
yeah, conductivity it shows because if you see carbon atom, right, what is its valency? 4.
Yeah,
So carbon, if you
4.
see, it is 1s2, 2p4.
1s2.
So you know this SPDF, sorry,
Yes,
yeah.
yes. Yeah.
So,
PX, PY, PZ,
so,
all
so,
are half filled. PZ is actually
so if
having
you
two
look
electrons.
at the carbon arrangement in graphene, so it is somewhat like this. Okay. So it is like an hexagon in graphene.
Ah, okay.
Now this hexagonal form, so here is an orbital, here is an orbital, here is an orbital. So orbital. So what happens is this s orbital. So I'll just, the electronic structure is this: px2, 2py2, 2pz.
Oh, it
Okay,
is PX2 and PY2, is it? I thought PX1, PY1, PZ2.
pz2. Why? No, no. See, so this is, so this electronic structure that I have written, this just
Mhm.
for the sake of your understanding, it looks like this. So here one sheet of graphene sheet is there. Okay.
Yes. Yes.
So it is just one plane. The next plane will be bonded by, so next plane will be somewhat bent. So it is just another hexagon. There will be another hexagon. There will be another hexagon. So there will be the sheets of graphene. Okay, that is what your graphite is. Now if you look at here at a single carbon atom here, then the orbitals, it looks like this. So there is something called sp2 hybridization. So here
Yes.
sp2 hybridization, what it will do, it will take 3 electrons sp2. sp2 hybridization means this s electron will hybridize with these 2p electrons, and these pz electrons will be in this plane perpendicular. You're getting it?
Okay. Yeah.
So what it will do, amongst these valency electrons, so there are these 4 electrons, right? Amongst these 4 electrons, what it will do, it will give, so sp2 will have 2 plus 1, 2, 3. So there are 3 orbitals. So actually 3 orbitals are combining. So it will have, so 1 electron in each of this. One valence electron here, 1 valence electron here, 1 valence electron here, and the last valence electron will be in this pz. This electron, when you see, so it will have, so each of these will have this uh, z orbital which is free. So electrons can hop from here to the next carbon, to the next carbon, and so on. This, along this pz orbital, these electrons can hop on along the entire plane of this graphene sheet. That is why it has very high conductivity. You got it?
Okay. Got it.
Yeah, but in diamond, what happens? It is sp3 hybridization. sp3 hybridization means the 4 electrons will be, so this is, let's say, carbon, and this is, so it is, so there will be 4 bonds to each carbon. It will be a tetrahedron shape.
Yeah.
So all the electrons are used up in bonding. There is no free electron. So that is why graphene shows high degree of anisotropy, and it is basically because of the crystal structure. Is that
Why
clear?
here SPZ? How did it get empty? Sorry, how it got filled here? Because uh, here the 2p x y z, all three have one electron.
All 3 have, sorry.
The diamond.
In diamond,
Yeah.
sorry, I just messed up something. So it will be like this actually.
Yes.
The filling will be somewhat like this.
Correct. Exactly. That's what I thought. That's what I was saying in the initial time.
Yeah,
It
it
should
is
be
actually like
px
this.
pyp.
Yeah.
Yes. Yeah.
So actually, when we feel the electrons, no, it will have that. There is this rule called what is that rule? Hund's rule of maximum spin. If you remember, I don't know if you know that rule.
Yeah. Yeah.
So the way we have to feel is, we have to feel the 1 electron
One,
here,
one, one.
1 here.
One, one,
After
and then
this maximization
1,
will
2.
happen, then we go to the next. So SPX1.
Exactly.
Yeah. So okay. Yeah. Thanks for letting me. I mean, that is why I'm thinking how. Okay. It is now
I
clear,
remember
right?
that from the school books.
Yeah. It is from school only. Like, yeah. So this Hund's rule of filling that we have to apply.
So in the diamond, what is the difference, sir?
In diamond, what? Okay. So now here sp2. So in case of sp2 hybridization, what will happen? All these 3 electrons will be used up. But in sp3 hybridization,
Yes.
1 s and this, what is this sp2? When we say this sp2 hybridization, this 2 refers to 2 of the p orbitals. When we say sp3 hybridization, all these 3 orbitals will be used up.
Yeah.
Now carbons, 4 of So carbon will have 4 valence electrons, right? So
Yes.
each of the valence electron will be used up. So one valency electron with this carbon, one valency electron with this carbon, one with this carbon, one with. So four of them are used up in bonding.
Yeah.
So there is no free electron to conduct.
Okay. So here the since the sp2 is happening, px and p2 becomes full and pz becomes free.
Yeah, the pz will have that one single electron, right? So here in sp3 hybridization, what will happen? sp3 hybridization will take 3 of the valence electron and one valence electron will be there in the pz orbital. That pz orbital can hop on in that seat of the graphene from one pz to the other pz. You can think of it as like graphene is like this in a plane, and pz orbital is coming out of the plane and one underneath the plane. These are the two lobes, and electron can hop from here like that to all the entire seat.
Yeah, I'm still not fully getting it, but yeah, I
Yeah,
get the uh, free electron theory here, but I'm not fully getting the hybridization here.
yeah, but you can just think of it as just graphene is a 2D material and it has conductivity. It
Got it.
conducts nice. But maybe if you read
I
something
got
up,
it.
you will just get to know.
I'll
So
go and read it. Yeah.
yeah. So what my point was, just a minute. I will maybe. Yeah. So if you, I mean, just to show you, sp3. So you see this, right? How it is happening? Let us just see
Yeah.
a particular.
This is sp2, right? Yeah.
Yeah. See these red orbitals. These are in a single plane. We can just watch the video
Yeah.
maybe if
See,
it's.
here I understand sp2 because what is happening is the pz is leaving away its electron to the py, so that px and py becomes full and pz is free to move.
In this
That
hybridization,
is what is happening in this.
Uh, just hold on. What if?
Yeah.
Yeah.
In case of
In case of.
sp2, what's happening is, see, px and py both are becoming two electrons, so that pz is empty and it becomes free and it is in the up and down of the plane of out of plane in the interaction, so that it actually can freely move. That I understand. Pz becomes empty in this
It is
case.
not empty. It
That
will
means
still have that one electron.
it is half filled.
Yeah, it is
Half
half
filled is a
filled.
stable.
No, it
Half
will.
filled is a stable condition, right?
Half filled is a stable condition. So we saw from this filling, right? It will still have that one electron, which will hop around in that uh, from pz orbital to the pz orbitals, so on. It will just hop around.
Okay.
I mean, you got it. But
I'm not very much understood that, but yeah,
you can look into
get to
some
read about it.
videos in YouTube or something, or so.
I'll do that. Yeah.
Yeah, that will help. Okay, so what about this eighth question?
An electron, which was earlier confined to 0.2 nanometer region, is later freely moving in 1 meter space. After a certain time under this condition, it has no confinement at all.
Yeah.
After a certain time under this condition, it has no confinement. Assumption based on observation or energy of electron is increasing with time. Energy spacing level is decreasing with passage of time. Temperature of material is increasing. That's a good point. Temperature of material, yeah. So when the temperature of material is increasing, it expands and then it becomes liquid.
Uh,
C is true.
C is true. Okay, let us first look at what is the first
A
option.
and C is true.
A and C
A
is
and
true.
C are
Okay, so why do you say, first say why is A true?
A is true because it is increasing. Electron is energy of the electron is increasing with time.
Energy of the, how do you know that energy of the electron is increasing?
It's actually, the energy electron which was earlier confined to zero point 0.2 nanometer, which had a for example, it was within, we are within that,
Yeah,
and if the boundary walls are broken, it becomes 1 meter, for example, zero point
yeah.
0.2 nanometer to
So
1 meter.
when it is a letter freely moving in 1 meter space, that is the space of a nearly free electron region. Okay. So energy, it was
Yeah.
earlier, earlier it was in zero point 0.2 nanometer, which is of the, this is of the order of few angstrom, right? 2 angstrom. 0.2 nanometers,
Yes.
2
Two
angstrom.
abstracts. Yeah.
So it was here. Then the energy increased, and it become this nearly free electron level. After a certain time, when the energy level is somewhat this, then it is no more confined. So the energy
Yes.
is actually increasing in time. From here, it become here. So this energy of the electron is increasing time is correct. Now energy
Yeah.
spacing of the level, energy spacing is here, this. Delta E is,
Yeah.
it will have that 1 by A square term. Now here
Yes.
the energy level spacing is 1 by L square. You're getting it?
Yeah.
So
Yeah.
and here it is like minus infinity to infinity. So there is no
Plus
energy
infinity.
spacing
Yeah.
at all when it is free. 1 by,
Yes.
I mean what, infinity, it is wrong to write infinity. Very large value, very large value. So it is no energy gap at all. So energy spacing
Yeah.
is actually decreasing. 1 by A square, then with time, increase in time, 1 by L square, then increasing time, it becomes 0.
Yeah.
So energy spacing is decreasing in time.
But for some reason, they did not consider this answer as a positive answer. You see this? Either it can be A and B, but A and B is not given as option. Oh, B and A are true. Oh, okay.
Got it?
Now
Temperature of the
A and
material.
C also.
See, temperature of the material is not actually playing a role in. So temperature comes into picture when you have a bunch of electrons. Bunch of electrons,
Mhm.
and it is a statistics about when do you say that a particular temperature is reached. A particular temperature is reached when there is no energy exchange between uh, between a reference system and your system that you are considering. We look at the energy exchange between two systems, and when the
Mhm.
energy exchange is stabilized, we say that the temperature of both the systems are same. That's what we do. So temperature,
Equilibrium.
yeah, temperature is a statement about the equilibrium. It is not about the heat or energy. So here
But
the,
here in this case, why this phenomena will happen? For example, an electron which is bound needs energy. Energy has to come from some form. For example, we are talking about um, some external factor is giving that energy to
yeah,
add to that so that it can become Fermi, or it can go to the level of the what do you call it, energy which is L, and it can go to the energy which is n infinity.
yeah.
What is giving that energy to the system?
So that we
That
don't
is the
have
temperature
to
probably.
worry. So energy can be given in any form. It can be given as a form of light. It can be given as a form of like it can be given as a form of heat as well. But that we don't have to worry. Any form of energy
But
will
the
do.
question here, yeah, the question they have asked is assumptions based on the observations are.
Yeah. So how, if the temperature of the material will increase, then how is it going to
So
affect
the
the?
energy is going to be available for it will get more kinetic energy, for example. And with that kinetic energy, it can actually move faster. And the boundaries, for
See,
example, I take a metal. Simple, I'll take a metal, for example.
see the
A
thing is,
metal,
the no, no, see. the statement that the temperature of the material is increasing is not same as the statement that the material is gaining energy.
Yeah.
I mean, you are getting it right. What it means is temperature of the material is increasing is not the same as temperature. The system is material is gaining energy. That will happen only if the specific heat of the material is positive. Like there is some statement has to be there about the specific heat, which is not here.
Yeah. True.
So unless specific heat is mentioned, a temperature has to. It is a statement about the equilibrium. It is nothing to. It has. It is. It doesn't have to do with the energy of the system as such.
Sure. Got it, sir.
Yeah. And in like last classes we saw right. Even all the energy levels can be filled when certain temperature is reached. Like so, those are the statement about the equilibrium and statistics. So that way C and D are not the correct answers. Yeah.
Okay, sir.
So what about the ninth question?
Ninth question. When only one end of string is tied, wave of any wavelength can move on it, but when both ends of a string are tied, then wave has more restriction imposed on it wavelength. Does it hold true for a practical example of a violin string of length around 20 to 30 centimeter? Violin string has both ends tied.
Yeah.
So yes, because both strings are tied at both ends.
Yeah, correct.
Yes, because the violin strings are made of metal. Should we say that?
No, it is because of the confinement.
Yeah. Okay.
Okay. This is the correct only correct answer is the because the strings are tight. That confinement is really necessary. What about this?
Anisotromy in a material depends is due to the periodic arrangement of ions and atoms in the solid. Enforce electrons to feel different potential at different locations. Results in same magnetic properties in different direction. Isotropy is magnitude and direction, so last is not correct. Enforces electrons to feel different potential at different location. That I do not know what it means. Depends on the size of the sample, doesn't matter. That is also not correct. A is not correct. Um, Only B seems to be correct, but I don't know about C. D.
Is due
C.
to periodic arrangement of ions. No, it anisotropy. See, periodic arrangement is there, but it has to say that the periodicity is different in different directions. So that sort of
Ah,
thing is not indicated from here. But it enforces electron to feel different at different locations. Instead of this statement has to be actually like, different directions. But like we'll go with
yeah,
this.
directions.
Yeah, we'll go with this option because
It's
like
due to periodic arrangement. Periodic arrangement will not work, is it?
yeah, periodicity has to be also. Uh, it is due to. I think that will also work because unless the periodicity is there, that how can anisotropy will come out? Because there is this periodicity is there only because of this periodicity only this anisotropy is there. So once you enforce the periodicity, no. So let us
Yeah.
even take a highly symmetric like this. So the
Yeah,
properties along this will be different from properties along this
correct.
because the lattice spacing is here like more than that compared to this. So as long as you have periodicity,
Yes.
you this anisotropy will be there.
Yeah. I only thought B, yeah, C, I didn't understand, but yeah, different locations probably I need to consider as different directions. Yeah.
Yeah. Okay, so that's all. Thank you for
Thank you,
joining.
sir.
Yeah.
I may take a little bit of time next week with little bit on Fermi Dirac and the other Dirac
Yeah, yeah,
equation
sure,
of
sure, sure, no problem.
Maxwell Boltzmann.
Yeah.
Just, for 10 minutes, I'll just touch upon this.
Yeah, sure.
Thank you, sir.
Okay, thank you. We'll end the session.